good morning or evening or whatever time it happens to be for you. It's late for me. Let's do lecture 14. It's page 1 of something. I don't know how far we'll get tonight. Let's see what we can do. Lecture 14. This is starting Unit 4. This is the last unit. We're going to look at some highlights out of chapters 7, 8, and 9. And then we'll look at chapter 10 just briefly and add chapter 10 to the final. But for exam 3, we're going to start with, in the Hibbler text, chapter 7, where we start talking about internal forces. We define internal forces. And so the basic idea here is that any member, body, truss, mutant potato, etc., anything you want to write there, anything has internal forces and moments. And that's the end of that sentence. Any member, body, truss, etc., anything you can imagine has internal forces and internal moments. And that's what we're going to look at in this chapter. Is we're going to kind of, I'm trying to adjust my light just a little bit there. We're going to look at these and say, how do we find those? How do we quantify those? Now, and we started to see a little bit of this in chapter 6. That's really what we're looking at. Is we're looking at internal forces within trusses and internal forces within frames and machines. And we talked about this concept I'm about to mention here. When we look at the entire, and rather than use this whole thing here, I'm just going to say whenever we look at the entire body could be a truss, a member, mutant potato, whatever you want it to be, but body is just a generic term. When we look at the entire body, these forces and moments cancel themselves out. As we're just going to say, follow Newton's third law. And if you're like me, when I was an engineering student, I had a hard time maybe differentiating which law was which. Well, the third law is the action-reaction law. And so what we're saying here is that if I look at a structure, like a truss, for example, when we do method of sections, we cut through a truss and we said, well, if we don't cut through the truss, the internal forces are not exposed. I'm just looking at trying to find reactions. But if I cut through specific members of that truss, then I expose their internal forces. Now, trusses are kind of a special case, and we start with those first because there's only forces in a truss, and those forces are only directed along the axis of the individual members. Here, whenever we cut through any particular object or body, there's going to be both forces and moments that are going to get exposed, and then we have to account for them. And if we take, if I were to cut through this pen here, I would right here on this band, then I would expose an internal force in the X, the Y, and there's also an internal bending moment. Because notice, I'm putting a pretty good amount of force on this, and this guy really isn't bending too much, because when I do that, there's a certain amount of internal bending moment right there. And if I analyze this by cutting right there, when I've loaded this up, and I just look at, all right, tell me how much the bending moment is going on in there. Steve, why in the world do we want to do that? Well, if I wanted to know when this thing's going to break, I need to know when the internal bending moment exceeds the strength of the plastic threads that are holding this thing together. That's how I would analyze the failure. Statics is the first step in that process. We first have to be able to figure out what are the forces and moments that are internal that we can't see when we look at the entire object because they're equal and opposite on each side of the cut. If I cut it right here, there's equal and opposite bending moments here and here that when put together are canceling out. Right? Hopefully that makes some sense. And so that's basically what we're going to describe here is when we cut through the member, and I put cut there in quotations because we're not actually going to make a physical cut, we're just going to make a pretend cut. When we make this pretend cut through a member, we need to draw and quantify the exposed forces and moments. And that's really kind of the whole idea behind this chapter. In 2D, and for the most part, these rules hold true in 3D as well. In 2D, you're going to have what we call the shear force. We're going to denote that as a lowercase letter V, as in Victor. Lowercase v, this is the internal force in a body, we'll say, internal force in a body that is perpendicular to the long axis. So whichever direction this thing is longer, in the case of this pin here, we would treat this pin kind of like we would a beam, and we would say, well, if I have this as my longer axis here and I apply a certain amount of force and I make an arbitrary cut, the shear would be the internal force perpendicular to this long axis here, as opposed to the normal or thrust force. Some texts will often call this the thrust. A lot of times our text likes to call it the normal. This is the internal force in the direction of the long axis. Again, if we take this pen, because it's here and it's handy, the thrust or the normal force would be the force directed along here. The shear force is the force perpendicular to the direction of the pin. And then, as we mentioned, you're going to expose both forces and moments. So basically this is, if I put the pin in the X direction, the shear is in the Y. The normal force, or the thrust, which we normally just use capital N. Sorry, I should have snuck that in there earlier. Those are our forces. And then in 2D we simply have the bending moment, which we'll call M. And this is simply the internal moment. Okay, so let's, a very simple example here. unless we're not going to put any numbers on this yet, we'll just keep it very simple. We'll put a pin on the left, put a roller over here on the right on a horizontal surface. We'll call this A, we'll call this B. Let's draw a couple of forces here. Let's put force F1, let's put force F2, and let's say we've got some arbitrary point C in here. And if I were to cut through this beam, this member here, right through point C, again, in quotes, cut. It's an arbitrary artificial cut. If I then look at the two sides of this beam, now I've drawn a cut right there, roughly at point C. When I draw free body diagrams to the left-hand side of the cut, I would have AY and AX, my pin forces there. I would have F1, because F1 is included on this left-hand side of the cut. And right here at the cut, I have now exposed a shear perpendicular to the beam, a normal or a thrust parallel to the long axis of the beam, and a counterclockwise bending moment, M. And what happens if I look at the other side of the beam? And I'll be honest with you, most of the time I look at the left-hand side, but you can. Nothing wrong with looking at the right-hand side, but we need to follow a sign convention. And the typical sign convention is this, that if I'm looking at the left-hand side of the cut, right, I should say, yeah, if I'm looking, this is the left-hand side of the cut, this is the what we consider the positive direction for these three quantities. If I'm looking at the right-hand side of the cut, that is my normal force, because these need to be equal and opposite. My shear I've drawn down here, so over here on this side, the shear goes up. And because the moment here is counterclockwise, the moment on this side needs to be clockwise, equal and opposite. And I've got F2 being applied out here. So, if we look at this, now I've got, and by the way, I could draw a free body diagram of the whole thing. If we want to look at the number of equations here, F1, F2, AY, AX, and B. So I can write three equations for this free body diagram. I can write three equations for this free body diagram, and I can write three equations for this free body diagram. Right? In theory, I've got 1, 2, 3, 4, 5, 6. I've got a total of 6 unknowns. In theory, I could just solve these two free body diagrams, but it's much more common that I would go ahead and just find my reactions straight out if I can, or at least find as many reactions as I could. Even if I had a pin on both ends, I probably could find AY and or BY with the two equations I could write here. It just depends on what I'm working with. So I could probably find at least two of these, even if I had a BX over here, which I don't in this case. So even coming into this one with AY in hand, you still wouldn't be able to find all of them. But you see what I'm saying? We have enough equations here that I could write between these free body diagrams to get quite a bit done very quickly. And now, let me lay down. I'm going to mention the concept of 3D cuts. This is, again, L14. It's going to be page 2 of something. I'm going to mention briefly how we would go about this in 3 dimensions. If I have some sort of a 3-dimensional beam that I make an arbitrary cut in, right? So here I've made an arbitrary cut in this 3-dimensional beam. And shape this in just a bit, so you can see what I've got there. Okay, this would be, of course, the long axis of the beam. You would have you would still have a normal force. You would still have a normal force. But in basically the normal force would be in the y direction, if you would, as I've drawn it here. That's putting the long axis kind of in the y direction, x-axis being this way. So I would have, perpendicular to that, I would have a shear force in the x direction, and I would also have a shear force in the other perpendicular direction. So if the normal or the thrust is in the y, then your shears would be in the x and the z. If your beam or your member is going in the z direction, your normal would be in the z, and you'd have a shear in the x and a shear in the y in that case. But in this case, I've drawn this normal is in the y, where the thrust force is in the y, and the shear would be in the x and the z directions, the perpendiculars. And then I would actually have a bending moment vector, so I would have components in all three directions. If this is y, so this is closing, so this is positive, I would have a bending moment in y, I would have a bending moment in x, and I would have a bending moment in z. So I'd have I would have a moment vector in 3 dimensions, so I would need to be able to figure out the x, y, and z components of that bending moment vector to do a proper analysis. Again, how is this going to help us? If I have some sort of structure in 3 dimensions and I need to figure out where along this thing it's going to fail based on how I've applied forces to it, these bending moments are going to help me determine where this thing is going to fail. We'll learn more about that in the strength of materials or mechanics of materials or design of mechanical components course later. Again, statics is where we start laying the groundwork, the foundation, pun kind of intended, for this material. All right, that's a little over 15 minutes. We're going to stop there, and I'm going to start uploading this one.